Hey everybody, welcome back to another fun and exciting geometry class. Today we're going to be on page 146. Page 146 in your books, we're going to be talking about intersecting circles and concentric circles. Intersecting, what does it mean to intersect? Well, it means that they cross each other. Interesting, if a circle intersects with another circle, it has 2 points of intersection. Where a line can have 1 point of intersection, but because of the curvature of the circle, they have to have 2 points of intersection. And they can only have 2 points of intersection. So if they have 1 point in common, then they don't intersect, they just touch each other. So if they have 2 points in common, then they are intersecting circles. Take a look down here at the screen. I've got theorem 41 written out for you. When two circles intersect each other, the line of center is the perpendicular bisector of the common chord. What does that mean? Well, I'm glad you asked. So if we put a common chord in here, that one's close. Let me try it one more time. That's a little better, okay? And so that's the common chord. It touches the circles there where they touch each other at their points of intersection. And then if we take and we put what does it say? The line of center. What is that? Well, we talked about it last class. That's the point from the center to the center, okay? So if we connect a line of center, then that is a perpendicular bisector of the common chord. In other words, right here, this is going to be a 90-degree angle. That's a right angle, that's a right angle. There's other things that happen here. For instance, you get a isosceles triangle right here and right here. So that's some interesting things that happen there. But the thing that this theorem is talking about is the common chord. The line of center and the common chord cross each other in a 90-degree angle, a perpendicular, and it's also a bisector. So here's the other thing about this. It also cuts this line in half. So if you were to measure this, let's say that this whole line right here, from here to here, was the yellow line is so A and B. So we say line AB equals 8 inches. Let's just say that. Well, when we put this common chord in here, it's going to cut it, and that's going to be 4, and that's going to be 4. We could call this point C. So then we would say AC is going to equal 4, and CB is going to equal 4 as well. It's bisected, it's cut in half. Again, on your future proofs and things like that, you are going to be using that. So kind of file that away, and make sure that you remember that anytime circles intersect each other, when you draw the common chord, and it doesn't matter where the circles intersect each other, top or bottom, it doesn't matter, left or side, right side, they always form this perpendicular bisector of the common chord. The common chord is when you join the two center points. Okay, so that's page 146. That's lesson 3.11. Go down and now look at 1.47, or excuse me, page 147. There we go. And that is 3.12, concentric circles. What's a concentric circle? Look here. It says concentric circles have the same center point. So look, here's the center point. They share the same center point. Think about times that we've seen this. We see this like on a bullseye when you're trying to hit the target, maybe with the bow and arrow or with the pistol. You're trying to shoot and you're trying to get it right there in the target. Well, it has concentric circles, and typically the next one's a little smaller, a little smaller, a little smaller until you get right in the very center. That's where you want to hit. You want to hit the target, the bullseye. In your book, it shows an interesting thing, page 147. It shows a drop of water. Think about that. So you take a little bit of water and you drop it into a pool, into a glass filled with water, something that's very still, very stationary water, and you drop that one drop and it hits and it forms concentric circles coming out from where the water droplet hit. and there's a picture of that there in your book on page 147. Concentric circles are used really all over the place. They're used in construction, architecture, design, all over the place. So very important concept right here. Concentric circles. They have the same center point. Now, if that's not the easiest lesson that you've ever had in the history of math, I'm just going to tell you right now. Look at page 147, 3.12. It says concentric circles, and then it says circles which have the same center point. That's it. Done. That's crazy, right? Well, I'm going to do something that I don't normally do here on the recorded videos. I am going to do a few of the exercises with you just to kind of, make sure that you kind of understand this basic concept. So, first question that they give you, can intersecting circles have the same center? Can intersecting circles have the same center? So think about this. So I've got a circle here, and I've got another circle here that are intersecting. So they got to intersect each other at some point. Is it possible for them to have the same center? Well, let's put a center in this one. Let's put a center in this guy. All right, that's not perfect center. Let me do a little better than that. All right, that looks a little bit better. Now, anywhere I go, unless I make it concentric, and concentrics are not intersecting. So if I make it intersecting, anywhere I go, this circle is going to have a different center point. You know, it can get close, but you're never going to have a center point the same. Okay, we can make a snowman. Okay, but well, sorry about that. I digressed right there. But you're never going to have a circle, two circles that intersect with the same center point. It's not possible. All right, second one. Can congruent circles be concentric? Can congruent circles be concentric? So what's a congruent circle? Well, a congruent circle is a circle that's the same size as the other one. Let me go ahead and just copy this circle right here. All right, so here's my here's my congruent circle. Okay, now this one is congruent because we copied it, so we know it's the exact same. What does concentric mean? All right, concentric means shares the same midpoint. Well, can it be concentric? Well, intersecting, intersecting, intersecting. Whoa, wait a second. What if we put it right back on top of that? Can it share the same center point? Yes, it can. Yes, it can. But there's only one circumstance that it can do that. So, if it shares the center point, what else is also true? That's the second part here. If so, what else would also be true of them? What else? They would also be what? Okay, coinciding. There's the other C word. Seems like geometry has all kinds of C words, right? Congruent, coinciding, concentric. It's like, oh my goodness, there's too many C words here. But yes, they would be coinciding, or they would be occupying the same exact space. Okay, now if you made one smaller than the other one or something like that, then they could. But if you have congruent means same size, same shape, then in order to be concentric, they have to coincide. They have to be on top of each other. All right. And then the last one, let's do number 3. And we're not actually going to do a whole proof right here. I'm just going to kind of walk you through this and just talk about it. So it says, prove the radii of two circles drawn to the points of tangency of a common tangent are parallel. So here's our circles, two circles. Here's our common tangent. Okay, remember these from a couple lessons ago? There's our common tangent. Now the question is, what about when we put a radius in there? Okay, so we're going to put a radius in this one. And the radius that they're asking us for is the one that goes from the center of the circle to the point of tangency. Notice it says drawn to the points of tangency. Okay, so center of the circle, because these are radius, or these are radii, and then to the point of tangency. All right, now, if I'm looking at that, it looks like it's parallel, but they're far away, so it's hard to know, are they exactly parallel? How would we prove that? Well, what do we know about common tangents? We just learned it a couple lessons ago. What we learned about them was that the radii from the center point to the point of tangency is always going to be what? It's always going to be perpendicular. What else do we know about perpendicular and parallel? We know that if, let's say we have a perpendicular. If we have another line that's also perpendicular to that same line, what do we know about these two lines? Yes, they're parallel, okay? And we have that already in a corollary or a theorem. You'd have to look back and find the exact one. But what we have is we have two lines. We have a line here and a line here. And they are both perpendicular to the same line. And because of that, we know that those radii would be indeed parallel to each other. Okay? And then you would prove that using that theorem from back there where we learned that. And yeah, pretty easy little proof right there. I'm not going to take the time to actually write it all out, but that would be the kind of the gist of how you do it. All right? Well, I'm trying to make up stuff to make this video longer, but I can't. We're all done. That was a short lesson. Actually, we did 2 lessons in there. So hope you learned something. Hope you were able to kind of follow those exercises. Do some more of those exercises. Prove some more things in there using concentric circles and different tangents and different things that we've been talking about, intersecting circles, common chords, all those things. Okay? If you have any questions, always just put it right there in the comments, and I hope you have a good one. We'll see you later. Bye-bye.